So bi-connected graph is what we want to test given a connected undirected graph. And we have reduced this problem to an equivalent problem of enumerating articulation points. Which we have now further reduced to that property. So X is an articulation point, then there has to be a child Y whose subtree doesn't have a back edge to ancestor of X. Okay, so that property inspires us to define high points. So high point of V for a vertex V in the graph is the highest DFN highest ancestor Z of V such that W to Z is a back edge and W is in the subtree of V. Okay, so for a vertex V, high point will be the earliest ancestor, the node Z which is earliest and definitely before V in terms of DFN, to which there is a back edge from a descendant of V. Okay, and go over all the descendants W. So again, pictorially, it is just these connections. So from the root, you are going to Z, which is an ancestor of V, and in the subtree of V, there is a W node from which goes a back edge. Okay, so in this picture, you have to pick the minimum possible Z. That's the high point. Okay, so in this picture, the highest Z above V is what you are interested in. That will be called a high point of V. So this is happening with respect to the vertex V. Is that clear? Okay, so now what we are interested in is in a pseudocode which for every vertex V stores high point V in an array. So yeah, but before that, so the above properties done in the class before lunch. So the above facts can be rewritten as the following theorem. So internal node X in the DFS tree T is an articulation point if it has a child Y such that the high point of Y is what? How do you rewrite the property that we had here? in that picture we had that blue property. A child y is there whose descendant is connected with the ancestor of x. How do you express it now using high point? Yeah, simply an inequality. Give me an inequality. Compare high point with DFN. The high point is an articulation point if and only if high point is greater than equal to, right? It's greater than equal to DFN of x. Or is that a mistake again? Yeah. That's correct. So it should be less than. It's an articulation point, so this what I wrote was correct, no? Because the highest point is actually below x or below. So if you delete x, then the graph will be disconnected. So this is the simple, this is just one inequality. So if you have high point and DFN arrays, then this is all that you have to check to enumerate all the articulation points x. Okay, so this is the exact condition rewritten with the high point array. So this basically means that the high point of y is not an ancestor of x. Okay, so when high point of y is greater than or equal to DFN, then it means that in the picture it is below x. So you don't go to an ancestor of x. So there is no way to bypass x. So if you cannot bypass x, then x will be an articulation point. Is that clear? So this sums up what you saw in the last class. Okay, we'll now just follow from here to get the pseudocode. But then now the question is, how do you calculate this this new array, high point? So that needs one more idea. So as you are doing the DFS tree, DFS traversal, how do you plan to update this high point when you reach a vertex V? You update it recursively. Okay, so when you go from V to a child, W prime say, so then the W prime's high point potentially will contribute to high point of V. So as you move forward, you will be refining the array high point. Okay, so you do this recursively. And DFS is already a recursive code. So you will see that everything will mix up very nicely. So the idea is just do this recursively. So example is these relationships. So high point of V is the minimum over all the neighbors of V. So whatever you had before the value of high point V, Obviously, high point V, you will start, this array will start with an initialization of infinity. Right? So highest point in the beginning is infinity, which is at the bottom, below the bottom of this picture. And then as you get more and more information, it will move up. And by the end of the DFS computation, it will go to the as close to root as possible. So it's a minimization step. So previous high point V, you will take minimum of that with the W that you have learned. Okay, so this is basically capturing the information from the child. Okay, so when you go from V to W, W's information can be useful in updating information of V. Okay, that's the recursive step. And there is one more case. What if this is a back edge? What if this one is a back edge? So the DFS tree took some other path. To parent of V. So DFS actually came via parent of V, and then the back edge. So this edge from V to W actually is a back edge in the DFS tree. So that's the other case, right? So there are these two cases in recursion, whether W is a child in the tree of V, or whether W is an ancestor of V in the tree. What is the update in this case for high point of V? Yeah, very good. So here you have to compare it with this new information, the back edge that you are seeing. Is this back edge helpful in going closer to the root? Right, so DFN of W will be important. So whatever is the value of high point V that you know, if DFN of W is smaller, then that should be updated. So this is minimum over the back edge. With DFN of W. So in the pseudocode, depending on what you are seeing, use one of these updates, and recursively the high point array gets, it improves. Okay, and in the end you have the correct high point. So once you have the correct high point array, then will come this theorem in the pseudocode. You will basically rely on this theorem. So suppose you have high point array and the DFN array, of course. How will you check whether X is an articulation point or not, if all the arrays have been correctly computed? What is the check in the pseudocode? Yeah, but do you want to go over? Yeah, so actually children will only be as many as is the degree of X. So you just check for all the children, what are their high points, right? So that is a small check. So in the end, in the pseudocode, you will see just comparisons of all the children Y with DFN of X. Okay, so that's the set of all the ideas lines that are needed, and now you can see the full pseudocode. Okay, so let us write that down. So let us call it DFS articulation point. So this will be updating. It does DFS on the vertex V in the connected undirected graph G. It will basically, we'll be modifying the DFS GV code that you saw before. On top of the data structures that were there, now you have also the parent array, the high point array, and the articulation point array. Okay, so this pseudocode will maintain, in addition, these three arrays. Parent is basically to remember the DFS tree explicitly. So for a vertex V, parent of V will be the parent in the DFS tree. That was not there in the first pseudocode, so we will introduce that here. High point is what we defined, and APV will be true if and only if V is an articulation point. Okay, so AP will store flags, true or false. Okay, so what you will do is the visit array. So V is now visited the first time. So make it true. DFN, so the number here is the timestamp that was there in DFS. So that's the same, DFN ++. And the new update is high point of V. Since you have just started with V, you don't know anything, so just set it to infinity. That's the initialization. So now look at the neighbors of V. So that's the for loop. If W is new, unvisited, right? So this is the case of the first kind of update. So from V you are moving to a neighbor which is new. Okay, so here you will have to use the first update equation. So that will be set the parent of W to V, do DFS on W, high point of V as before, right? So do the minimum. So let me not repeat that. So the same variable and the same this high point V, look at its minimum with high point W. Right, so this is the first kind of update because you are going down to W in the DFS, and but this is also a good place to check whether V is an articulation point, right? Because W is a genuine child in the DFS tree. So you can do a check right here whether the high point of W is greater than or equal to DFN of V In that case, what happens? So you have found a child which is certifying that V is an articulation point. So APV you set to true. Yeah. Okay, and then the other kind of update, the update which is in green, because now W visit W is true, right? So you are actually going back. That's a back edge. So do the else if. So when you do else if, what you want to check is the following. So let us actually draw the picture for this, what is happening here. So here you have W, parent and V. And a back edge. Okay, so now we are in this situation and we are checking whether the parent and W are different. And what should you do in this case? That green, the second type of update. So high point of V here is high point of V with DFN of W. Why did we do this check of parent V not equal to W? What happens when they are equal? Sorry? It's not a back edge. Yeah, so we are just avoiding that case of this orange and blue edges being the same. Right, we don't want that. So for back edge, we have to actually go above parent, because parent and V are already, there is an edge. So just that boundary condition is being checked. Otherwise, this is just a back edge check and then you update high point V accordingly. So if the current value of high point V is not good, DFN W is further up, then the update will happen. Okay, you are improving on high point. Okay, and this I guess completes it. So you have DFS AP now over. And so you can now do DFS AP traverse. Okay, so DFS AP on a vertex is already is present here now in all the details. DFS traverse also you had, which was the code that would call DFS GB. So corresponding to articulation point, you can write that also. It's basically the same. It's the same as DFS traverse. It just initializes the arrays and then it calls on V, DFS APV. Okay, so this is the full, all the modifications on DFS procedure. Okay, any questions about this? So what do you think is the time complexity of this? So there is only one for loop here, and that for loop for a V goes over the neighbors, right? So this is just, the time here is degree of V many times. Okay, so this is, this for loop is going degree of V many times, and the updates are all trivial. They're all constant time updates because everything is stored in different arrays you immediately access. So you just have to do this for all the vertices V, so sigma degree V over all the V's, right, which you know is number of edges. So that's what you get. So time is upper bounded by degree of V over all the V, which is upper bounded by order M. This is a connected graph, connected undirected graph, so M is anyways at least n minus 1. Right, so this is really just order M. So the time is as much as the number of edges of this pseudocode. So based on this pseudocode, the theorem that we have shown is due to Hopcroft and Tarjan from many years ago. So given this graph G, all articulation points can be found in order M time. Okay, so linear in the size of your graph, which is the given by adjacency list, remember. Linear in that much, you can actually find all the articulation points, and hence you have an algorithm for biconnectedness. Okay. So not only you will be able to check whether your network is robust, if it is not robust, then it will also give you all the weak points in the graph. Is that clear? So, okay, the proof of correctness for this is whatever we have done in the previous 2 hours. Okay, all that is the proof. So you just have to join all these subplots to make the big story. The properties we have seen proved, they characterize all articulation points. And then the pseudocode finds them. Okay, so basically the pseudocode correctly, you have to show that it correctly finds this high point. That is the first property you have to show. So those parts you should do as an exercise. It's just a repetition of what we have done. But you have to prove it in order. So you have to first show that pseudocode correctly computes high point V for every vertex V. Okay. That's a recursive proof. So once high point V has been correctly calculated, then the pseudocode you have to basically use the property that this check high point of W. So is there a child whose high point is at least DFN of the parent? Right, that property means that V is an articulation point. So that is one lemma that we have shown. So embed that lemma. So hence articulation point array will also be correctly computed. Okay, and finally show that the for loop is running degree of V many times and sum of degree V is number of edges. Yeah, this is only DFS of V, but then DFS of AP traverse will go over other vertices. So overall, you will have to take a sum of degree of V for all V. Okay, so DFS traverse is the main code, the initialization code, and the code that calls DFS V. And for DFS V is you have this analysis of time in terms of degree of V. So just combine all these things and embed in the proof. Say that again, parent of W is V. Yeah, this is already calling DFS of W, that is correct. Yeah, so actually already the connected component of V will be completely seen. So recursively it is calling, yes. Yeah, so already this code DFS AP has complexity order M. Yeah, so those are the things that you have to work out. I mean, in the sense, just combine and write the proof in sequence. Yeah, so here is your recursive call happening. So degree of V many iterations plus you have a recursive call. So since there is a recursive call, obviously you have to make this observation that we have made in the basic DFS code, that a visited vertex, DFS is never called on a visited vertex. Right? DFS is only called on unvisited vertices. So this for loop, inside the for loop there are other for loops, inside which there are other for loops, but overall edges are not repeated. Right? So those things you have to include in the proof. Okay, so I think this much should be enough for you. Those are the detailed hints to complete this theorem. Okay, so Hopcroft and Tarjan's theorem is mainly for this biconnectedness, and then out of this we get DFS, a more general algorithm which solves other problems. So you will see some applications in assignments and exam problems. To cover all of them, use the internet. Okay, so find other applications read about other applications of DFS. So BFS, DFS have tons of applications. We can only cover very few. Okay, rest you can read up. Again, the modification required I don't expect them to be big. With small modifications, you can actually solve many of the problems to do with graphs. Okay, so yeah, any questions at this point? So this finishes graph traversal topic, and now we'll start a new topic which is we'll go back to BST. So BST or red black tree and so on. Since this is a data structures course, so we'll teach you a number of data structures. Most of them are tree based. Okay, so you have seen before midsem binary search tree, which was balanced, and then you saw a more complicated implementation of that via red black tree, which may not be balanced, but still it does whatever we wanted it to do. So now we will design fancier and fancier tree-based DS, okay, till it becomes so complicated for you that I will stop. Okay, so many things will be out of the scope of this course. So what is it that we want more from tree-based DS? So what if we want to improve the time order log n time to constant time? Okay, so the property of BST and its examples was that we were claiming all the operations that were there in the mathematical modeling of the DS could be done in log of the size of the DS, which is n elements are there, or n records are there, right? So records are big records, but they have keys. Keys are distinct. Arrange them in this tree-based DS. And then there is a set of operations that you want in the mathematical modeling. We have shown rigorously that all these operations can be done in maximum order log n. So what if we wanted all of them to be in constant time? Yeah, so that is the thing we want to do now. And we will not be completely successful, but we can come quite close. Almost all the operations ultimately can be done in constant time. So for that, we have to look at a new data structure, which is called heap. There are many kinds of heaps. So a heap H is a tree data structure. Okay, before that, I should say that constant time access was available in an array, right? So we'll now try to actually combine a tree-based data structure with an array. Okay, so we've actually, before midsem, we went from array to binary search tree, and now we'll try to go back, okay, and take a different route. So have you seen heaps before? Okay, nobody has seen heap. Yeah, so heaps can get quite complicated. So let us start with a simple example of heap. Heap in general is a tree data structure where the value at a node V is less than the value of the children. For all the vertices. Okay, so heap is a tree-based data structure. So it's basically a tree where again the nodes store records have keys are distinct, and when you look at the key, or which I am calling here value, at a node V, it has to be smaller than those stored in the children. Is this a BST? Why not? Yeah, so this in particular is allowing you to have something like this. Right, so this is a valid example of a heap, because you can see that left child is not less than the parent, which in this case is less than the right child. Okay, so there is only 50% of the property is satisfied, not 100%. But still, the parent is smaller than the children, union of the children. Okay, and it may not be binary, so there might be something else also. So just heap will mean something like this: any number of children bigger than, all of them are bigger than the parent. Okay, so that's the, so this is a relaxation of BST. Is this clear? It's not a BST. So what do we want from this data structure? We have to first do the mathematical modeling. So query operations, query is only one. You want to implement, you want to query for the minima in this DS. Okay, Prateek is here, so that's not good news. Okay, so min is smallest key in H. Okay, so like in this case, so where is the smallest key stored in the heap? At the root, right? Even if there are subtrees here, even if you have these subtrees, still because of the heap property, heap axiom, minima will be at the root. So this query operation is a trivial operation. You just return the value of the root. Okay, so that is the only query operation. Update operations will be harder in this data structure. So first is just creation, that's trivial. So create a heap, empty heap. So pointer to null. Okay, so that creates just a pointer H, which is pointing to a root which is null. Next is extract min. So this is like min, except you want to delete the min from the data structure, right? Which means that you want to delete the root. So these are updates, right? So you have to actually modify your DS. So delete the min, that is root of H. Then there are some fancy ones, which is first is decrease key at node P by delta in the heap. Sorry? Yeah, so P is the node which has a key, of course, the value. You want to decrease it by delta. So, I mean, it's clearly makes sense to call this an update operation, but you have not seen this in previous data structures. I mean, this decrease key is essentially replacing a value in an given node arbitrarily, right? That value will suddenly be changed to something else. But when it is changed, you still have to maintain the heap axiom. So you have to, there will be chaos in the heap, and you have to again make it into a heap. So decrease the value of P by delta and maintain the heap. Right, the same thing goes without saying in extract min also. Delete the root, but then make it a heap again. And the last one is merge. Two heaps are given, 2 pointers. You have to merge them and make a single heap. So merge the 2 heaps into 1 heap. Okay, so this is the mathematical modeling. And we will implement this in a binary heap. Okay, so in this course we will see only one kind of heap. There are many kinds of heaps. Some of them are extremely efficient, but we cannot cover them in this course. So we'll just do the baby version of heap, which is the binary heap. This already will have some advantages over BST, but not the maximum advantage that we want. So our heap, the tree will be binary. Will be close to a complete binary tree. And stored in an array. Okay, so it will have, as I said, both the properties. As a tree, it will be in particular close to a complete binary tree. And it will not be stored via pointers, but stored in an array. So all the mathematical modeling will happen on this array, maintaining the heap structure somehow. So we'll do that on Wednesday. So let's stop now. Any questions?